A.J.S. Well, April 27, 2018, for the 15th year in a row, Opportunity and the Mars Exploration Rovers (MER) mission drove into the spotlight during an afternoon session at the 49th Lunar. Known by its acronym, LPSC, is where this niche of the space community regularly communes and where this MER-class robot field geologist is treated with reverence worthy of a veteran. Drawing scientists, professors, and students from around the world, this annual conference is where the latest, greatest research in planetary science is presented and the craziest, most far-reaching, thoughtful theories flaunted. Under the banner Mars rover results I, Depositional and Environmental History, 6 scientists took to the podium on March 22 to present Opportunity's findings in Perseverance Valley so far, as well as their analyses and the evolving thinking about the strangely unique formation that defines Endeavour's west rim at Cape Byron. Although the MER presentations followed 6 talks on Curiosity's recent findings, Opportunity's Starbot power and the science delivered kept the room filled to the end. By the time the session was over, they succeeded in leaving the audience in a cloud of metaphorical dust, wrapped in the fog of another Martian mystery. Opportunity has been exploring the western rim segments of the 22-kilometer, 13.7-mile, diameter Endeavour crater since August 2011, racking up some 12 kilometers, more than 7 miles, climbing, driving, and sliding around, in, and through several of them. With Perseverance, however, the robot is blazing another new trail into ancient Mars, charting Earth's first on-site look at a feature that from orbit looks like it was carved by water flowing downhill. The objective is straightforward: study the valley's morphology or shape and its compositions, and determine how, and if possible approximately when, it formed. NASA, JPL, Caltech, MSSS, and MMNHS, L. Crumpler Endeavour crater Opportunity drove up to the west rim of Endeavour, a 22-kilometer, 13.7-mile, diameter crater, at Cape York, in August 2011. After finding signs of past water and ancient clay minerals there, the robot field geologist roved on, and is currently in Cape Byron conducting the first-ever study of an ancient geological feature that from orbit looks like it was carved by water. The base image is a mosaic taken by the Mullen Space Science Systems context camera on the Mars Reconnaissance Orbiter. Larry Crumpler, of the New Mexico Museum of Natural History. North is up. From the crater rim crest, or notch as it appears in images, Perseverance extends downhill at about a 15-degree angle for about 200 meters, about 219 yards toward Endeavour's interior. Along the way, it breaks into an anastomosing pattern, or, in other words, it branches off in different directions that look like a river system. In the first images taken of it by the HARIS camera on board the Mars Reconnaissance Orbiter, MRO, this place screamed water. That's why we went there, said MER project scientist Matt Golombek during a recent interview. Moreover, whatever first created this feature was generally thought to have occurred at some point during the ancient Martian epoch 4.1 to -3.7 billion years ago, called the Noachian period. That's the time frame when Mars is believed to have been wetter and more like Earth, with rivers, lakes, streams, and perhaps an ocean. Sometimes, however, impressions from orbit are not so clearly confirmed when viewed up close by a robot field geologist. The MER scientists are scientists though, and they assume nothing. As a rule, long before Opportunity even pulled up to Perseverance in May 2016, the approach to researching this distinctive place was declared decidedly unbiased and intentionally simple. We're going about this with multiple working hypotheses, said MER principal investigator Steve Squires, of Cornell University. That has been the mantra ever since. NASA, JPL, Caltech, University of Arizona, Perseverance Valley. This orbital image was taken by the HARIS camera on the Mars Reconnaissance Orbiter, MRO, which is overseen by principal investigator Alfred McEwen, a planetary geologist and director of the Planetary Image Research Laboratory, PIRL, at the Lunar and Planetary Laboratory at the University of Arizona. You can see the notch in the crater rim in lower left quadrant of image, and the valley's anastomosing or branching pattern becomes apparent in the center of the image. It's an approach, geologically speaking, that is well-traveled and long-proven, as Rob Sullivan, a MER-Athena science team member, also of Cornell, pointed out. The method of multiple working hypotheses, written by American geologist and educator Thomas Croter Chamberlain, 1843 to 1928, was first published in 1890 in the journal Science. Basically, Chamberlain argued that when approaching a complex problem, carrying multiple working hypotheses encourages greater objectivity, said Sullivan. He also theorized that many geological problems are best explained by several different processes acting at different times or simultaneously over history to produce landscapes as we find them in our times. Chamberlain went on to found and edit the Journal of Geology, serve as president of the University of Wisconsin, president of the American Association Advancement of Science, AAAS, and a director of the Walker Museum at the University of Chicago. During the last 125 years, it has become a classic, published many times in different formats, and its principles guide and influence research integrity to this day. One of the biggest mistakes you can make as scientists is that attitude, "I wouldn't have seen it if I hadn't believed it," noted Squires. You don't want to fall into that trap. The thing to do at this point is keep an open mind, multiple working hypotheses, and let's just let Mars tell the story. NASA, JPL, Caltech, Cornell, ASU. Top of Perseverance. Toward the right side of this scene is a broad notch in the crest of the western rim of Endeavour crater that looks like it might once have been a spillway. In the spring of 2017, Opportunity left tracks while checking out the top of Perseverance Valley, which descends out of sight from the notch. This scene includes troughs that may have been formed by water, wind, or faults caused by the impact that created Endeavour or something else. The objective is to determine what force or forces formed Perseverance. Opportunity is now halfway down Perseverance and Mars is still talking. Beyond the sometimes slippery slopes of the gravelly terrain on which Opportunity is roving, the team's challenge lies in the fact that Perseverance is the only geological feature of its kind at Endeavour. There is nothing anywhere else in the rim that looks anything like it. The valley's singularity is an outstanding characteristic, Sullivan said. That's the good news, right? The bad news? This poses important challenges to all candidate origins, including water, he said. So uniqueness is making the task of uncovering the story of Perseverance one of, if not the greatest Martian mysteries that Opportunity and the MER science team have undertaken. Nevertheless, in tight, on-point presentations, the 6 lecturers of MER research at LPSC this year reviewed some solid geologic studies, laid out a number of key findings that reveal an evolution in the team's thinking and proved once again that there's nothing quite like a good Martian mystery. Steve Squires, PhD MER principal investigator, Athena science team led, James A. Weeks professor of physical sciences, Cornell University. It's a work in progress. Steve Squires cut to the chase. Then he launched the MER talks with a high-speed walkabout of the evidence the Athena science team members have found to date at Perseverance Valley and the implications that data may have for solving the mystery of what it was that created this unique geological feature. NASA, JPL, Caltech, University of Arizona, left, A.J.S. Rayl, right, Steve Squires and Mars Exploration of Perseverance MER principal investigator Steve Squires, of Cornell University, right, led off the MER talks at LPSC in March 2018 with a high-speed review of the various discoveries that Opportunity has found during her road trip into Perseverance Valley, left. At the time of the conference, the rover was about halfway down the length of the valley. Click to enlarge map to see rover's route through Sol 5000, mid-February 2018. Showing an overhead view of the valley as it cuts through the rim of Endeavour, Squires described Perseverance as having a braided sort of appearance, and a very distinctive look that is the consequence of some kind of fluid flow. At the approximate halfway point on her journey, however, Perseverance is still a real mystery. We have multiple working hypotheses, said Squires. When we started we had 3 hypotheses: dry avalanche, debris flow, some kind of fluvial river transport. We can test these hypotheses by looking at the features on the ground. Since last May, Opportunity and the team have been looking at all the features on the ground, as well as imaging the morphology. While they have found evidence that seemed to point to past water, they also uncovered other potential contributors to the original working hypotheses that would be detailed during the conference. Out on the plains above the top of Perseverance Valley, west of the crater rim, are some very broad, shallow troughs that more or less seem to terminate at the top the rim crest, as if it would be the kinds of things through which fluid flows, and then spill down. Squires said, pointing to the top of the notch in another overhead image. But there's a serious challenge for this hypothesis. The top of Perseverance actually slopes up, he said. Mars is a weird place, but not so weird that water flows uphill. Still, it has been a few billion years or so, give or take. You could solve this if this surface was originally horizontal and then part of it went through some compaction, he said. Tim Parker, a MER Athena science team member and a geology lead, would expound on that as he offered up his lake spillover theory later in the afternoon. Once Opportunity got into the valley, the scientists found the topography to be really very subtle, Squires said. A lot of it isn't filled with soil. The rover has also found plenty of visibly scoured outcrops, at a site named La Bajada, where 2 distinctly different outcrops are separated by the valley path. The scientists even found breccia outcrop with telltale wind tails that really caught our attention," said Squires, recalling how Opportunity popped 2 wheelies to be able to hunker down over this outcrop and check it out up close. "This wind tail or flow tail indicates the direction of flow," he said, pointing to an image of the flat rock at La Bajada. "And that direction is uphill, since wind blows radially out and up the crater rim." Most of the science team members view this as pretty strong evidence of wind erosion. Squires said, "This doesn't mean the valley itself has been carved by wind, but it certainly at least points to Aeolian erosion overprinting after the valley itself formed." Aeolian erosion was one of the multiple working hypotheses Rob Sullivan would focus on. Later in the afternoon, NASA, JPL, Caltech, Cornell, ASU grooves, stone stripes, and an answer blown in the wind from troughs to stone stripes and scoured rocks. Opportunity has found all kinds of geological goodies in Perseverance. The PanCam team at Arizona State University, ASU, processed the image of the troughs, left in false color, a technique scientists use to better discern the various geological elements in the scene. The troughs and the stone stripes, middle, remain enigmas for now, but the etched rock bacilla, right, at the La Bajada site really caught the scientists' attentions, because its flow tails indicate direction of erosional flow. "That direction," said Squires, "is uphill. And that points to wind erosion, not water flow." In the troughs, where the soil is, the scientists found distinct linear arrangements less than 1 meter across. Squires said, "What geologists refer to as stone stripes, you can see these parallel ridges across, and the ridges are composed of coarser grains with finer grains in them. We immediately think these could be some kind of paraglacial features like the stone stripes found in a number of places on Earth where there is shallow subsurface ice, like on Mauna Kea, Hawaii. But when you look at these things closer, it doesn't hold together so well," he said. The science team needed to find out if Perseverance Valley is a place where ice could be stable, or if there is something unique or special about Perseverance Valley that would cause these features to be here. Squires explained, "Because we don't see stone stripes a lot of places." Mike Mellon, a planetary geologist and geophysicist and associate research professor in the Applied Physics Laboratory at Johns Hopkins University, stepped in at MER Deputy Principal Investigator Ray Arvidson's request to help with some thermal modeling. The objective was met. "The answer is no and no," Squires said. "So what are they?" Sullivan suggests these stone stripes could be mega ripples, an extensive undulation of the surface typically tens of meters from crest to crest and tens of centimeters in height or larger. Somewhat like the frozen waves on sandy beaches or seabeds on Earth, you'd think something really big, but mega ripples simply means they're developed from material that has been fractures and saltation, said Squires. "We may in fact be seeing something new here." NASA, JPL, Caltech, J. Sorensen, D. Davis 5,000 Souls members of the MER Ops team worked together to help Opportunity celebrate her 5,000th day on Mars by taking her first ever selfie with her microscopic imager camera, left. About a week later, the team had the robot take an additional lower tier of pictures for the mosaic to include the rover's right wheel. James Sorensen processed the image presented here. Davis colorized it using a realistic Mars palette. At LPSC, Steve Squires gave a shout-out to members of the ops team at JPL, right, who have helped make the MER mission possible. Another key observation the scientists have been making is the number of trough areas where there is a distinct difference between one side of the trough and the other side. This is suggesting there may be a fault here and that the erosion that formed Perseverance Valley may be in large measure structurally controlled, Squires explained. It could be wind erosion, as opposed to any kind of water erosion. "We've got to take that fairly seriously actually." Crumpler's presentation on the structure of the crater and the fault zones in Perseverance and Sullivan's talk on the potential contributions of reactivated faulting and wind processes would soon expound on how seriously, while the origin of Perseverance is still a work in progress, Squires personally ruled out the dry avalanche theory. The downhill slopes are too gentle, at 15 degrees, and the rover has seen no deposits of anything, indicating a past avalanche. That leaves water or fluvial transport, wind, and debris flow, as he viewed it, still among the multiple working hypotheses. There was more to come, more to go, and new observations about how planetary forces, like people, sometimes work together. Larry Crumpler, Ph.D. MER Science Team, Research Curator Volcanology, Space Science, New Mexico Museum of Natural History and Science, Associate Professor, University of New Mexico. On the first geologic traverse ever conducted by a rover within the rim of a large impact crater, Opportunity has driven approximately 12 kilometers, more than 7 miles, in the western segments of Endeavour. Along the way, Larry Crumpler has been studying the crater's structure, as well as the rocks, outcrops, and troughs to understand how the structure agrees with the actual physical characteristics the rover is finding on the ground. In his talk, he laid out evidence that the West Rim segments and Perseverance Valley are strongly controlled by faults and fault zones created at the time of impact. New Mexico Museum of Natural History. Larry Crumpler and the mapping of structure and faults. Larry Crumpler's maps of the structure of Endeavour are providing evidence that its rim segments are probably controlled by faults caused by the impact that created the crater. As the rover descended into Perseverance Valley, he continued mapping and uncovered potential faults and fault zones. "I think increasingly we're seeing the possibility that the valley is controlled by some sort of major fault," he said. As Opportunity descended from the Cape Tribulation Rim segment and roved to Perseverance, Crumpler studied geological characteristics documented in the images the rover sent home. "One of the large-scale characteristics is the segmentation of the crater rim," he said. "When you actually look at the rim, it consists of these little segments that are on the order of a couple of 100 meters long and maybe 100 meters wide," Crumpler continued. "They tend to be offset from one another, they tend to have different orientations. And when viewed together, one gets the impression one is looking at some sort of structural division in the makeup of the crater rim." Moreover, as Opportunity has traveled from one rim segment to another, the nature of the outcrops, the basic fundamental geology was changed in very subtle ways, chemically and structurally, he said. On those treks, the rover has crossed transition areas, where the terrain changes and where the scientists have seen intense alteration characteristics and the most interesting geology, another indication that a major structural change happened, or perhaps a major fault abounds the segment. Until recently, the MER scientists have seen very little evidence in the outcrops that show unequivocally a fracture or fault is associated with these transition areas. "It's been somewhat frustrating," Crumpler said. Since entering Perseverance Valley, however, Opportunity has been returning images that show distinctive lithological divides and linear formations that, he noted, are the characteristics of linear fractures that are controlling things on an outcrop scale. NASA, JPL Caltech, New Mexico Museum of Natural History. Crumpler finding faults in Perseverance. In the graphics above, Crumpler shows Opportunity's route into Perseverance, left. "The important point is that we've mapped out these fractures or faults from La Bajada," Crumpler said at LPSC. "Basically, they bound the margins of the South Trough. The faults are the blue lines, right image, and our volcanic rocks and linear outcrop in the middle between them look suspiciously like fault zones. The base for these graphics are orbital images taken by the Harris camera on board MRO, which have been stretched vertically so scientists can better see the terrain. Different kinds of rocks near each other, and especially those with a sort of boundary between them, often indicate the presence of a fault to geologists." As Opportunity has descended the approximate 15-degree slope of Perseverance Valley, the rover has also found the juxtaposition of different rock types have aligned downhill. The strip of terrain that separates the outcrops of La Bajada, where bright, flat rocks on the northern side contrast with lumpy, darker rocks on the southern side, where Opportunity found the windtails that point uphill, looks suspiciously like some sort of fracture, said Crumpler. "There's some sort of zone here that's very disturbed looking, and when we sat on it, we really could not say what it was," he said. But off to the side there was another very linear feature that is several centimeters wide, characterized by a half-meter wide, very long zone of parallel red and gray materials. Like a fracture or alteration zone, this linear feature cuts through the impact breccias and moves downslope. As we moved farther down the valley, it continues for some 50-60 meters, and this feature is trending parallel to the same La Bajada feature," he pointed out. NASA, JPL Caltech Cornell, ASU La Bajada's fault. As Opportunity drove downhill in Perseverance from Station 1 to Station 2 in September 2017, she drove right through this area, named La Bajada after the stop on El Camino Real de Tierra Adentro, the old, 2,560-kilometer, about 1,591-mile, trade route between Mexico City and San Juan Pueblo, NM, the team's naming theme since entering the valley. What drew the scientists were telltale signs of erosion on the bright outcrop right. The rover drove back uphill to investigate. Further research by Larry Crumpler indicates La Bajada is likely a fracture or fault. When Crumpler mapped the potential fractures and faults of La Bajada based on the physical characteristics at the site, he found that a fault bounds the margins of the South Trough. That says perhaps the valley itself has actually got significant fractures or faults and is actually following the current track, he said. With the data in hand, Crumpler postulated, there could be a fault running through here and it could be wind erosion that formed the valley. But, he added, the real question is Perseverance Valley just a graben? A graben, by definition, is an elongated, depressed block lying between two faults. An example of a graben on Earth is a rift that cuts across land. Crumpler was quick to note that he thinks the formation of Perseverance is more complex than that. However, he concluded, there is evidence that the valley structure was controlled by some sort of major fault that likely influenced fluid movement in the crust and may have controlled trough margins. Rob Sullivan, Ph.D. MER Science Team Member, Senior Research Associate, Cornell Center for Astrophysics and Planetary Research, Cornell University. After an introduction underscoring the value of the multiple working hypotheses approach the team is taking, despite the understandable interest in the possibility of flowing water, Rob Sullivan focused his presentation on evidence showing the potential contributions that fracturing in aeolian or wind abrasion made in the formation of Perseverance. Rob Sullivan, A.J.S. Rayl. Rob Sullivan in the power of wind and fractures. From the outset, the MER Science team has been working with multiple working hypotheses to try and determine how, what, and when Perseverance formed. Rob Sullivan presented his research showing that two forces have visibly impacted the morphology of the valley, wind and faulting. Advancing on Larry Crumpler's talk about fractures, he proposed that the Perseverance trough system might have been formed by a network of ancient fractures and faults that reactivated, conceivably multiple times. Sullivan's presentation began with a quick familiarization tour of aeolian abrasion features on Earth, including wind-altered rocks in Coachella Valley, California. Wind-driven sand impacting rocks can completely change rock shapes by eroding away a great deal of material while applying special, diagnostic textures to rock surfaces that remain, he said. Earth-based examples as a basis for comparison, he turned to Mars, showing examples of aeolian abrasion along opportunities traverse at Meridiani Planum. Beyond the pervasiveness of this process at Meridiani Planum, Sullivan's main point was that aeolian abrasion happens fast. That's fast geologically speaking. Ejecta-blocks thrown out by recent impact craters on the wind-rippled plains that the rover crossed to get to Endeavour have been eroded on timescales of hundreds of thousands of years, similar to the rate of ripple migration. Sullivan pointed out, these timescales were quantified to less than 1 million years in constraints on ripple migration at Meridiani Planum from Opportunity and Harris observations of fresh craters, a paper written by MER project scientist Matt Golombek, and for which Sullivan was a co-author, published in the Journal of Geophysical Research in 2010. Well, that raises a couple of pertinent questions, and would seem to damn the flowing water hypothesis. If aeolian abrasion is that effective in this valley, presumably formed in the first half of Martian history, how could it have survived looking like a river system more than 2 billion years to today under the onslaught of the constant winds? Alternatively, if water carved Perseverance Valley more recently, so that the trough system remained recognizable as it is today despite degradation by aeolian abrasion, is it possible that there was flowing water in just this one location, and if so, then where did that water come from? Rob Sullivan, left, NASA, JPL Caltech Cornell, ASU. Blown away on Earth and Mars. Wind-driven sand can completely change rock shapes in a relatively short amount of time geologically speaking, said Sullivan, as he showed images of rocks that have been shaped by aeolian abrasion during his LPSC presentation. From the Coachella Valley on Earth, left, to a crater named Fram on Mars, right, winds have visibly altered the shape and textures of rocks. Sullivan illustrated these issues with close-up pictures of rock surfaces within Perseverance Valley that showed diagnostic aeolian abrasion textures, indicating wind-driven sand blowing up and out of the crater. This is inconsistent with any signs for water erosion acting downhill, he said. From Marathon Valley, another low-lying site that cuts into Endeavour's west rim in the Cape Tribulation segment, which Opportunity explored in 2015-2016 before heading farther south along the rim to Perseverance, Sullivan showed rather dramatic examples of aeolian abrasion. Wind processes have reshaped exposed rocks there, as well as planed off most of the valley floor, which, unlike Perseverance, is not soil-covered, he noted. Interestingly, the bare rock surface of Marathon Valley's floor is marked with a complex network of fractures at all orientations, many of them soil-filled, others not. Sullivan pointed out, some of the largest fractures are oriented downslope, toward the center of the crater. These are important features for comparison with Perseverance Valley, he added. Opportunity's views from within Perseverance Valley reveal that the potential traces of stream water flow seen from orbit turn out to be rather unimpressive features of very low relief. Essentially, these features are very shallow, soil-filled troughs between similarly low-relief outcrops, he said, in noting that these troughs share characteristics with sand-filled fractures seen elsewhere, particularly the features interpreted as fractures at Marathon Valley. NASA, JPL, Caltech, Cornell, ASU, S. Atkinson halftime picture show Opportunity took the frames that went into this panorama with her navcam in early March 2018. The tracks show how the rover has moved around this site, about halfway down the length of Perseverance Valley. Author and planetary outreach educator, Stuart Atkinson stitched the frames together and processed this image. A frequent image contributor to the MER update, Atkinson also contributes to the Planetary Society's Amateur Space Images Archive, and blogs about this rover's journey at his The Road to Endeavour. Sullivan proposed that the shallow, interleaved trough system of Perseverance Valley might have been formed by a network of ancient fractures and faults that reactivated after the potentially wet, warm climate of the Noachian period, conceivably multiple times, with long hiatuses in between, he said. Minor surface relief resulting from each reactivation, like from any upward displacement of one block relative to another, would be followed each time by erosion and reduction of the newly formed relief by aeolian abrasion and other weathering processes. The problem of Perseverance Valley's singularity remains, of course. Of all the fractures and faults caused by the impact that riddle the bedrock all through the Endeavour region, why would only those in the area of Perseverance Valley reactivate from time to time? Sullivan wondered. He wasn't sure, but he pointed the location of Perseverance Valley in a low area of Endeavour's rim between higher rim segments on either side. Sullivan speculated that a highland on one side eroding down faster through the ages than the highland on the other side might periodically focus some stress-adjusting fault reactivation in the more vulnerable area in between Perseverance Valley. Still, the heart of the issue, he pointed out, really is, how rare is fault movement at Meridiani Planum during the last half of Martian history? To explain the singular nature of Perseverance Valley, the team is looking for a process, perhaps faulting, fracturing, perhaps something else, that is very rare, but yet not entirely absent, Sullivan said as he clicked to one of the final slides of his presentation. NASA, JPL, Caltech rare evidence for fault reactivation. Opportunity took this image on Sol 1784 more than 3,200 sols or Martian days ago with her navigation camera, navcam. It shows a fracture that apparently reactivated recently enough to offset a large wind ripple, leaving the two sides misaligned. Displacement fault activation does occur, very rarely, Sullivan concluded. On the screen was a navcam picture that Opportunity took more than 3,000 sols ago that showed something indeed very rare, a fracture that had reactivated recently enough to offset a large wind ripple. One side of the ripple had become misaligned with the other side, with the fracture slicing in between. Displacement fault activation does occur, very rarely, and on the same time scale as ripple migration, Sullivan said. Therefore, it is comparable with the survival time of minor surface relief, such as recently emplaced impact ejecta blocks, against aeolian abrasion. While this observation seems promising, Sullivan did not seem entirely convinced. Opportunity is only halfway down Perseverance Valley, with many more observations to make, he reminded the audience. It was a closing comment that emphasized the point that the multiple working hypotheses approach is what's still driving the MER mission objective, something Sullivan had already summed up in his last slide. No conclusions about PV origin yet. Multiple working hypotheses. Collect more data. Timothy Parker, PhD, Athena Science Team member, Geophysics. Matching high-resolution orbiter views with projections of images Opportunity has taken on the ground, he presented his show and tell visual analyses conjecturing how this unique geological feature could have been formed by a short-lived flood that spilled over from an ancient lake to the west of the crater rim. NASA, JPL, Caltech, Cornell, ASU. Timothy Parker and Perseverance pondering Timothy Parker, MER Athena Science Team member, of JPL, left, has been a part of the MER mission since the beginning and, like a number of other MERsters, also does double duty on Curiosity. After years of anticipation, Opportunity